Welcome back to the series on statistics. In this video, we're going to be talking about moment-generating functions, but before we do that, we should remind ourselves of what moments are. And so, mathematically speaking, we know that the nth moment of a distribution, modeled off of some random variable, is just the expected value of that random variable to the nth power. But intuitively, we should think of moments as measurements that characterize some aspect of the probability distribution. And so, for example, the first moment of a distribution is pretty intuitive. It's just the expected value of that random variable. So that will give you the mean of the probability distribution, or where that probability density function will be centered. The second moment we know is going to be related to the spread of the data. It's not precisely equal to our conventional notion of spread, the variance, but it's definitely related. We know the equation that the variance is given by the second moment minus the first moment squared. First moment is just going to be some constant. And so this is just proportional to the spread of the data. It's actually equal to the second central moment. Beyond the second moment, we have the third moment that's related to something called skewedness, and the fourth moment describes something known as kurtosis. Some people call it tailedness of a distribution. But each one of these moments is going to contain some information that describes that probability distribution. And so you could think that if you were to make more and more moments of a distribution equal, then those distributions would start to look more and more similar. And so we're going to explore that with a little quick example here before we move forward. All right, so we're told to let x be a uniformly distributed random variable in the interval from 0 to 1, and y be a normally distributed random variable with a mean of 1/2 and a variance of 1/12. And we're asked what the mean and standard deviations are. Obviously, this question is immediate for y. The mean of y is directly given to us, and the standard deviation of y might as well have been given to us because we had the variance and it's just the square root of the variance. And if I was to rationalize this, on the bottom we're going to get, we could pull out the square root of 4, that's going to give us 2 times the square root of 3, and then we want to rationalize, so we don't want those irrationals in the denominator. So this is going to give us the square root of 3 over 6. Now for x, we actually do need to do a little bit of work. I've made a video on continuous uniform distributions, but the mean of a uniform distribution is just going to be the midpoint of the interval for which it's defined. And so here, the midpoint of 0 and 1 is just going to be 1/2. And so the mean of this uniform distribution here is 1/2. The standard deviation is the square root of the variance, obviously, but the variance here is given by the width of the interval squared divided by 12. So if you're curious about where those formulas come from, it's direct from the expected value definition, but I have a whole video on that, on continuous uniform distribution. So this is just going to be the width of the interval squared divided by 12. That will give us a variance, so we take the square root of that. Width of the interval here is 1, and so this is actually exactly the same. And so the point is here that both of these distributions, they have the same mean and they have the same standard deviation. So by definition, they're going to have the same first moment and the same second moment. And if you look at a graph of these distributions, obviously they're not the same. I mean, one is defined for all real numbers and the other is defined from 0 to 1. But you can kind of point out some similarities here. So the first thing to notice is it's pretty obvious. They're both centered at a point of x is equal to 1/2. So that's where that first moment comes into play. But both these distributions are also similarly spread out. And that might make sense as well. You could think intuitively, if you were to take these deviations from the mean for both of these distributions and square them, and then weigh them against the height of the probability density function for each distribution, and take the sum of all of those deviations across the entire interval, this is exactly what we're doing when we're computing the second central moment. You could think that when you're doing that, when you're taking these deviations from the mean here, and weighing them against you're weighing them much heavier for the normal distribution. Here you're weighing everything against a probability density function of 1, so you're essentially just summing up all of the deviations from the mean. But here you're weighing them against the green probability density function, so you could think the effect of weighing these smaller deviations more heavily could be canceled out somewhat by weighing these larger deviations much smaller, or much less heavily. And so you could think the effect of that would it could partially cancel out, and you would be left with the average of those effects would be equivalent to weighing them against some average height here that's somewhere in the middle. And so that's what we've shown mathematically. That turns out to actually be true. But you could imagine that makes sense. Just to kind of illustrate that idea, I plugged this into Desmos, and so you can calculate both of these second central moments for both of these distributions. Here, integrating from negative 15 to 15 for the normal distribution in this case is effectively the same thing as integrating from over all real numbers. And as you can see, this does indeed, the effects of these smaller deviations being weighted heavily do sort of cancel with these larger deviations of being weighted less heavily, and it does result in the exact same effect as finding the variance over this, or the second central moment of just the probability density function of 1 from the interval from 0 to 1. And so we've already had this information because we knew that the standard deviations were equal, we knew the variances were equal, but this is just an alternative way of calculating them, and it does kind of illustrate this idea that these effects sort of cancel out. And so the point here is that both of these distributions, although they are completely different, they do have things in common, and these are both related to these moments. And so you could think if both these distributions had more and more moments in common, the distributions would be more and more similar. And you could think if they had all their moments in common, that they would be identical distributions. And while there are some counterexamples to that, in general that does turn out to be the case. And so moment-generating functions, where they exist, are going to have enough information contained within them to uniquely determine all of the moments of a probability distribution. That's why they're called moment-generating functions. And so if you could show that two probability distributions have the same MGF, the same moment-generating function, then that's enough information to show that they have all the same moments, which shows that they are the same distribution. And now you might be thinking, you already have the probability density function. Isn't that enough information to show that they're the same distributions? The answer is absolutely. If two distributions have the same probability density function, same PDF, they're exactly the same distribution. The issue is that sometimes it's easier to show that two distributions have the same moment generating function than it is to show they have the same PDF. Particularly, I'm thinking of the case of the central limit theorem, where what we're trying to show is that the distribution of sampled means tends toward a normal distribution as you increase your sample size. You could think of the distribution of sampled means as the sum of several different random variables. Each of those random variables is one observation from the population. And as you take the sum of more and more of these random variables, we want to show that sum converges towards a normal distribution. And it's practically impossible to do that with PDFs alone. I'm not aware of any way to do that. But there are ways to do that, to show that with moment-generating functions and characteristic functions, which are basically the same thing as moment-generating functions. It's just we're getting out of the scope of the topic here, but the moment-generating function is effectively a Laplace transform, and the characteristic function is a Fourier transform. But we're not going to dive deeper into that. We're going to start talking about what these moment-generating functions are, but I just want to give some motivation for why we would be interested in describing these in the first place. Alright, so in order to derive these moment-generating functions, we're going to need two tools in our toolbox. The first is the law of the unconscious statistician, which is very commonly abbreviated as LOTUS. This rule tells us that the expected value of some function applied to a random variable is just going to be given by integrating over all values of support in the support for that random variable. You're going to integrate that function evaluated at some dummy variable multiplied by the probability density function for the random variable evaluated at that same dummy variable. And so the reason this is called the law of the unconscious statistician is because it just looks like it would work. That's probably what you would guess the expected value of some function applied to a random variable would be. At least that's what I've been told. That's where it comes from. But the proof for this is actually extremely complicated. Even just in the discrete case, you need to take several tools from functional analysis, and the meaning, it just escapes me, at least. So I'm incapable of teaching that. I will link some material in the description so you guys can see for yourself, explore that at your leisure if you're interested. But the linearity of expectation is the other tool that we need, and this one I actually am going to prove here. And so we have our proposition. It's that the expected value of a times some random variable x plus b times some random variable y is going to be equal to a times the expected value of x plus b times the expected value of y. And so I've already kind of started the proof here, but we're going to let x and y be random variables with joint probability density function f of xy, or given by f of xy, and we're going to let a and b be real numbers. Then the expected value here, by the definition of the expected value of ax plus by, this is just going to be equal to that we would integrate over all values in the support for both of these random variables. And here, just to preserve the meaning here, I'm not going to use a different dummy variable like I did substituting t for x here. I did this to avoid confusion because usually usually you would use an uppercase x for the random variable, a lowercase x here. But since this is effectively handwritten, that could get confusing. Here I actually am going to use a lowercase because I want to preserve the connection between the random variable and what's being represented. And so here, this will be, I'm just going to try to make this clear that these are lowercase and these are uppercase. But this is just going to be effectively a dummy variable. Plus b y multiplied by the joint probability density function of xy. And then we want to integrate this with respect to both of those dummy variables. And essentially all we're going to do is we'll distribute this joint probability density function across both of these. And then we're going to break this up into two integrals. And so the way that this is going to work is we'll have two integrals. The first one will be ax times the joint probability density function with respect to x with respect to y, plus the second one, where once again we have to integrate over both the support for both of these random variables, but here we're doing by f of xy with respect to x with respect to y. And then here, in this case, we can actually switch the order of integration here. And the reason we want to do that is because we want to pull this x out. And so here it's actually already in a way that we can do this. We could say that this is equal to, in this case, we could pull the b out completely since it's just a constant. So this would just be b times the integral. And then here we can pull the y out of the first integral since it does not depend on x. It's effectively just a constant when we're integrating with respect to x. And then this becomes y times the integral from f of xy dx dy. And now here I'm going to add some subscripts here because here we're integrating over all values of the support for x. And so I want to make it clear that this is the support for x, this is the support for y. And then this is going to be effectively the same thing. We're just going to switch the variables here. And so this we're going to integrate over the support with respect to x. And we pull the a out front. We pull the x out of the first integral, where we're integrating with respect to y over all values in the support for y of the joint probability density function. Here we're just switching the order of integration here just to allow us to pull out this constant. Now here, the key thing to realize here is that here we're integrating over all values in the support for y across the joint probability density function. So what is this going to give us? This will give us the marginal probability density function for x. And so what this is going to reduce to is we're going to get a times the integral over all values in the support for x times the marginal probability density function for x with respect to x, plus b, and then we're integrating over all values in the support for y, a dummy variable y, times the marginal probability density function for y with respect to y. And what are these? Well, this is just going to give us the expected value of x, and this is the definition for the expected value of y. And so this is going to be a times the expected value of, or I guess these are brackets, the expected value of x plus b times the expected value of y. And we're done. And so that shows the linearity of expectation, which is going to be important for these moment generating functions. All right, so now that we have those properties understood, we can move on to the actual definition of a moment generating function. This is it right here. For a random variable x, the moment generating function is given by just the expected value of e to the power of sx. And so that's kind of unassuming. It doesn't really seem, I feel like there's a lot of build up here, and maybe this doesn't seem like a big payoff here. But these moment generating functions, this when you take the expected value of this function evaluated with this random variable, these functions are going to have the property that the nth derivative of the moment generating function evaluated at 0 will give you the nth moment of the distribution. It's also important to note that the moment generating function is going to exist if and only if the expected value of this expression here converges for at least some values of s. So in other words, there must exist some epsilon greater than 0, such that for all s on the interval from negative epsilon to epsilon, and so this is just some region around 0, the expected value, this expression here, must converge. It has to be finite. And if this property is satisfied, then the moment generating function exists, and it uniquely determines that distribution, all the moments of the distribution. All right, so let's walk through this definition. I'm going to talk about this definition. I'm also going to talk about this condition here, because both of these are a little bit hard to wrap your head around, but they should make sense. This moment-generating function is essentially just derived from the Maclaurin series or the Taylor series for e to the x. So if you recall from calculus, we know that e to the x can be written as the infinite polynomial sum of 1 plus x squared over 2 factorial plus x cubed over 3 factorial It's essentially following this this sum here from k is equal to 0 to infinity, and we're doing let's see, what would this be? This would be x to the power of k over k factorial. And so this is that Maclaurin series for e to the x. So if we want e to the sx, we just plug that in for x here, and we're going to get that the expected value of e to the sx is just going to be equal to the expected value, and we're essentially going to have the sum here, the sum from k is equal to 0 to infinity of sx to the power of k over k factorial. But we know from the linearity of expectation that we can make some adjustments here with this expectation. We could essentially distribute it across each of these terms in the summation. And so this is equivalent to the sum from k is equal to 0 to infinity. And then we're taking the sum of these individual expected values. And then here I'll go ahead and distribute this exponent. And so this could be across the s to the k times x to the k over k factorial. And now here we can sort of take this s to the k and k factorial out of the equation here, since these are ultimately going to be just constants, especially since we're going to be evaluating this at some value of s. You have to remember that this is a value, this is a function of s, it's not a function of x. But the reason we want to factor out these two terms here is because then what we'll be left with is, and we can totally do this because this expectation operator is linear, so we can factor out these values here. We can treat them as constants, so long as we're evaluating this expression at a value of s. And we're going to get that this is equivalent to the infinite sum, k is equal to 0 to infinity of, we can factor out this s to the k over k factorial, and this is going to be multiplied by the expected value of x to the kth power. Now, this expected value of x to the kth power, that's just the kth moment of x. That's exactly what it is. And so we want to see if we could find some way of deriving this expression. And the key thing to realize here is that given that this is a function of s, this is just some constant. So if we were to take the kth derivative of this function with respect to s, if we took the let's see, how would you write this? The kth derivative with respect to s of this sum here, I'll just copy and paste it. The kth derivative with respect to x. If you were to evaluate this, we should remember from calculus, but if you don't, just consider the case of taking the second derivative of like s squared over 2 factorial. You could bring that 2 down, it will cancel, and then you'd be left with just s, and when you take the second derivative, it's just equal to 1. And in general, this is true. I encourage you to verify this for yourself. But if you take the kth derivative of this coefficient here is just going to be equal to 1, and we'll just be left with the expected value of x to the k. So if we take this expression, we still have the rest of these terms to contend with. But if we evaluate this at s is equal to 0, right, then every term before the kth term in the series, right, every term before that is going to go to 0. Because it will just eventually, by taking more and more derivatives, it will ultimately turn into a constant, and then when you take the derivative, it will go to 0. And given that it's part of the sum, it's essentially contributing nothing to the sum. And so all the terms before the kth term will go to 0. The kth term here, when you take the kth derivative, this coefficient will go to 1, and we'll just be left with this value here, the expected value of x to the kth power, which is exactly equivalent to the kth moment of x. And that's going to be it. It's just going to be equal to the expected value of x to the kth power. Every term beyond that is still going to have an s in it. In fact, the next term is just going to be s, and then the term after that will be like s squared to the divided by 2 factorial, something like that. But it's all going to have an s in it. And so if we take the kth derivative and evaluate it at s equals 0, every term before this kth term will go to 0, and every term after this kth term will go to 0, and we'll just be left with the expected value of x to the kth, which is the kth moment. And so that's how this function works. That's how we're getting the kth moment from this function. All right, so now we should have some understanding of how these moment-generating functions work. We know what their definition is. The last thing that I want to contend to, this is one of the hardest things to understand about this function, is this aspect here. There's this condition here that the MGF has to exist, and it only exists if it converges for some value of s. And so in order to actually demonstrate that, I wanted to do a quick little example problem. This is going to give us some practice with this idea, but also with deriving moment-generating functions. And then my original intention was to derive several moment-generating functions in this video. I think I'm going to move that to a separate video because I can sense the length of this video is already becoming pretty long. And so I'm just going to do this problem to sort of illustrate this idea, and then the next video I'm going to derive several more moment-generating functions for a couple other distributions. But here we're told, let y be an exponentially distributed random variable defined by the probability density function f of x is equal to lambda e to the negative lambda x. And so the way you would notate this, I know we haven't talked about exponential distributions yet, but we have the PDF here, so this is enough information to solve the problem. But you would just notate this as exponential lambda. And this says that y is an exponentially distributed random variable with a rate parameter. I think this is called a rate parameter of lambda, pretty sure. But this is the PDF here. And so this is defined on the interval from 0 to infinity. I think some people define this for all real numbers, but they have to use the unit step function. I don't want to bother with that since we're doing integration. And we're asked to find the moment-generating function of y. So let's do this problem. All right, so per the definition of the moment-generating function, we have the moment-generating function of x of this, I guess, of this random variable y. This is going to be equal to, here we need to integrate over all values in the support of the random variable. So per the question's specifications, we're going to be integrating from 0 to infinity. And then we want e to the s little y. In this case, this is just some dummy variable. It could be anything, it could be t, but it needs to correspond with the probability density function. You have to have the same dummy variable in both of these. And so this is going to be multiplied by the probability density function, e to the negative lambda y. And here we're integrating with respect to y. I'm just using y because it matches our random variable. And so here, this is relatively simple to compute. We're just going to move this lambda out, and we're integrating from 0 to infinity, and we can push these exponents together, the exponential laws, and so we're going to have e to the sy minus lambda y, and so that's the same as e to the s minus lambda y dy. And so actually computing this, to take this antiderivative, this is going to be equal to lambda times e to the s minus y, or s minus lambda y, over s minus lambda. That's an ugly lambda, let me fix that. And then here we're evaluating at 0 and infinity. And so here, consider what happens if s is greater than lambda. What happens in this case? Well, here in this numerator, we're going to have a positive exponent on e. And so if we're trying to evaluate e to the power of some positive constant times y, or times our variable that we're evaluating at infinity, this is just going to be infinite. It's not going to converge. But the key thing to realize here is that if s is greater than lambda, then this is going to diverge. This diverges. But if s is less than lambda, then what happens? Well, here in the numerator, we're going to get a negative exponent on e, and if you take the limit of a negative exponent, a negative exponential, as the variable goes to infinity, that's just going to converge to 0. So this actually does converge. And so in the case that it converges, this is actually the only case that we're interested in here. And so we'll say if s is less than lambda, then the moment-generating function of y is just going to be equal to, and then let's evaluate this. If s is less than lambda, this is some negative exponent, it'll just go to 0 at infinity, and so that's just going to be 0. And then we'll get lambda times, and then what is it going to be at 0? We'll do minus e to the s minus lambda, or no, we're evaluating this at 0, so this whole thing is going to go to 1, so we'll have negative 1 over s minus lambda. And so the more conventional way to write this is we distribute this negative across the bottom here, and so you just do that this is equal to lambda over lambda minus s. That's just distributing that negative here. And so this is our moment generating function. But the key thing to realize is that the only reason that the moment generating function is defined for this random variable here is because there exists some values of s such that this expected value, this integral that we're evaluating here, has to converge. You could imagine if this didn't converge for any values of s and it just diverged everywhere, then you could imagine that we would say that moment generating function didn't exist for that distribution. And this does actually happen. So we need to be careful, and that's what's meant by this thing here. That's what's meant by this condition. We need to have some values of s such that this expected value converges. And just to build on that idea a little bit, you might be wondering, well, what happens if s is greater than lambda? You could imagine plugging in values of s that are bigger than lambda here and seeing what happens to the function. But you could do that, but really the answer is it doesn't matter. And I'll tell you why. If you look up here, this condition is that there must be some range of infinite values that contains the point 0 such that this expression converges. Now, you'll notice there's no stipulation on how big this neighborhood of values is. It just needs to exist. And the reason is actually right here. It's kind of staring us in the face in disguise here on the right side. It comes from this Maclaurin series. All of the information that we care about, all of the information that's going to characterize our distribution is contained at the point 0. Now, it's not the function evaluated at 0 is not what we're interested in. It's the rates of change. And for us to evaluate these rates of change, there needs to be some interval of values contained around the point 0 such that the function converges. That needs to be the case so that we can evaluate the rates of change. Now, it doesn't matter how big the interval is. It can be infinitesimal because what we're doing is we're evaluating derivatives. So we're taking infinitesimal rates of change, very, very minute ones. So it doesn't matter how big this interval is. We're taking the limit as the rate of change, or as the change in y over change in x goes to, you take the limit as change in x goes to 0, the formal definition of the limit. And so no matter how small this interval is, it's never going to be smaller than the limit as epsilon goes to 0, which is essentially what we're taking when we're calculating these series of derivatives. And so this is all we need is this condition. All we need is there to be an infinitesimally small range of values about the point 0 so that we can calculate these rates of change and get these moments. Because these moments are what we care about. This is where all the information is that's characterizing our distribution. It's all there at 0, but it's concerning the rates of change. Also, this moment generating function is always going to be defined at the point 0. You could think if you take the expected value of e to the sx evaluated at s is equal to 0, when you put 0 here, this is just going to be the expected value of e to the power of 0, which is just going to be the expected value of 1. And the expected value of a constant is just a constant, so it's always going to be defined at the point 0. So it's kind of not interesting. We just need there to be a small range so that we can calculate these rates of change. Just because it's defined at the point 0 doesn't mean that the derivative is defined at the point 0. That's the condition that we need. We need the series of infinite derivatives to be defined there at the point 0 so that we can calculate these moments. I really hope that makes sense. I hope it's interesting. I think this stuff is fascinating, but that's the connection there between this condition, between the Maclaurin series, the reasoning behind where the moment generating function comes from, and I hope this gives some intuition as to situations in which the moment generating function would and would not exist, and I hope you can imagine in your head sort of there would be cases where s wouldn't diverge there would not exist this interval of values around 0 where the expected value of this exponential would converge. In the next video, I'm going to derive some more moment generating functions for different distributions. We'll talk about the normal distribution. That's going to be the hardest one, but we'll also do binomial and uniform. After that, we'll try to prove the central limit theorem using these moment generating functions. And then as we move beyond that, we'll just talk about how to practically solve problems involving normal distributions, because that's going to constitute a lot of what you do with statistics. And there's certainly easier ways to do that than having to plug in this giant integral into your calculator into Desmos every time you want to evaluate a probability of a normal distribution. And then as we move beyond that, we'll talk about confidence intervals and hypothesis testing, and that will conclude the first statistics course. Thank you guys for watching. I'll see you all in the next video.